Some of the other challenges that we had to start to deal with that were not apparent at all when we started the project. We were dealing in the south and we didn't have any of these features. But as we moved north into the boreal, when we started to look at the bare earth LiDAR data sets, we started to notice these very interesting features, these raised bog features. And so the LiDAR pulses that are sent down from the aircraft, they can only see the last return. They can only analyze the last return that they actually receive in order to try to develop the bare ground surface. But in these areas, we tend to have very large, fairly mounded peak domes. So from a topographic overland flow perspective, which is how the Whitter's mapping is derived, these features all appeared as dry islands, as domes. So we had to start to look at ways, based off of a LiDAR-based solution, to try to identify these wetland features and deal with them accordingly. So we started to look at a few different LiDAR-based data layers. So we had to look at the bare earth DEM, the full feature DEM, as well as the intensity information, which is basically a measure of the amount of energy returned based off of the absorption characteristics of the target. So the energy returned back to the sensor for each of those objects. So we'll now just talk a little bit about the pros and cons of each of these different data layers and some of the trials and tribulations that we went through to get where we are now. So the bare earth LiDAR is really the data set that's the most consistent across the large areas. So when we're just dealing with EMEND, we can have fairly good confidence that all these areas or all these data sets are going to be congruent. They're all spatially, the whole EMEND data set's probably been flown at the same time, same year and everything else, the same sensor. But as we start to imagine that this process has to be consistent across that whole 25 million hectares of scope, we start to look that there's different vendors, that there's different times of year, there's different leaf on, leaf off, all these different parameters, different sensors, all these different things that can start to impact the resulting DEM data sets and intensity data sets at the broad scale. So the bare earth LiDAR is basically the one that has the highest consistency. It's the one that has the specifications within the standards that the GOA requires. The specifications are based on the bare earth rasters. The vertical accuracy assessments are all based on bare earth. There isn't really any requirement from the standards of having proper tree heights within a full feature data set. So, from our perspective, the bare earth was probably going to be the most consistent and the most reliable data to use. When we had a look at the full feature data set, there's some pros associated with that as well. We can derive very easily some canopy height models. And these raised wetlands have some fairly characteristic vegetation structures. So we started to say, okay, well maybe we can start to tease out some information based off of the canopy information associated with some of these wetland features. Some of the cons, again, it can be influenced by the season and the year of acquisition. So leaf on versus leaf off, not as much of a problem in these softwood areas, but it can be in the large scale. As well as, if we have a certain tile that part of it was processed in 2008 and part of it in 2012, we're going to have substantial growth of the trees within those areas. So canopy height can be kind of a difficult thing to use. Now we're looking at the intensity image. So this is, again, the intensity of the LiDAR returns back to the sensor relative to the target object. So one of the issues with that, or one of the pros I guess we'll start with, is that inundated soils can have a fairly characteristic intensity value range. So you can see here that they do kind of stand right out where these wetland features exist. They tend to have a higher value for the inundated soil. But some of the issues are that this LiDAR intensity information is delivered as an uncalibrated data set. There are some vendors now, and some sensors now, that can actually create what's called calibrated intensity values. But the data that we received, or that you guys all received, can be impacted basically if you remember that the LiDAR sensor shoots its pulses down. Some are at nadir, so directly beneath the aircraft, and some are off at 20 to 23 degrees off to the side of the nadir, I guess we'd say. So there's going to be a further distance that pulse had to send before it's returned back. So just things in terms of the distance that these pulses have to travel, and different things like that, and the flying height, can all have implications in terms of proper registration and proper attribution of the actual intensity values for these. And again, leaf on versus leaf off, different sensors from Northwest versus airborne imaging, they use different sensors. At the large scale, we start to see various patchworks of these intensity rasters. So in terms of consistency, we would have had to come up with a methodology that was able to handle each of these different parameters from these different different data sets based off of their different characteristics. So that just for us didn't seem to be a very proper way to continue on with the project. But we tried. So we had a look at the intensity extraction. So what you see in yellow, or in green, sorry, is the intensity-based bog feature extraction. So it did a fairly good job, within a small scale. It did great. But as we started to expand this across larger areas, it started to fall apart. Again, for the reasons that I previously mentioned about calibration, as well as when we're looking at intensity values, and we're just trying to classify them out, there are other features that can share the same intensity ranges. And oftentimes, we found that a lot of these cut lines shared fairly consistently similar intensity value ranges to the wetland features. So there was going to be a lot of false positives with these. And as we all know, there's many of these transects that exist across the landscape. So it would have been a fairly noisy data set.
Could you tell us what type of vegetation is giving the different intensities? Is it the foliage of the conifers versus the leaves of the sedges or the mosses? What do you think is going on here?
As far as I know, it seems to be more the low veg, like the peats and things like that are causing these issues, because we have a lot of conifers throughout these other areas as well, right? We have conifers in through here as well, just a standard forested area. So it's still going to be a green, but it tends to be a different kind of green. And as we see in some of these, it might be kind of difficult to see, but it tends to be a lot of the lower vegetation that's causing this differentiation of the intensity values more so than the actual conifers themselves, from what I've experienced. I haven't dove that deeply into it, but that's what it seemed to be.
With the presence of standing water?
It may, but I don't believe so, because standing water, as you can,
moisture within there.
It's
reflecting as much of the light.
Yeah, it's more associated with the inundated characteristics more so than the open standing water characteristics, because if you have a look at this area right here, this is a lake, right? This is an open water feature. So the intensity value associated with that open water feature was different than the intensity value associated with these wetland features. So, and oftentimes those can be very, very noisy as well, because we'll have either total absorption or total reflectance because it just bounces off to somewhere else. So intensity values for open water features can be kind of problematic.
You had made a comment earlier that tall standing grasses, for example, might reduce the accuracy of the DEM, which might influence this.
Yes.
Have you looked at that, the differences in your DEM accuracy between, let's say, your forested areas and adjacent cut blocks, and just to see whether there really is a large difference that could be then reflected in the areas?
I haven't quantified anything like that, but oftentimes when we look at the bare earth rasters and we see a cut block relative to a natural forested area, it can be fairly apparent that there are differences within those zones. I haven't done any real analysis to see what the extent of that is and how much issue there is with that, but it's definitely, it can be seen, more so from different vendors, the way that airborne imaging processes their, it's all, if the bare earth extraction is going to be entirely based on the algorithms that a particular vendor employs to drive that bare earth surface. So from our experience, it seems that Northwest employs slightly different methods than airborne imaging does. So the bare earth, two companies could fly the same area with slightly different sensors and slightly different algorithms for that virtual deforestation, and they're going to come up with a different bare earth surface. So that's one thing that we started to kind of deal with as well, was the bare earth, although it's the most consistent, is still not entirely consistent. And the slash that can be left on the ground can be fairly dense in some areas of a cut, and so that can be problematic in certain areas. But as far as we've tended to find, the vertical differences aren't sufficient enough to really cause much problem. So hopefully that answers your question. Okay. So I guess we'll move on. So this was our intensity-based kick at the can for bog feature extraction. So next we went to the elevation-based extraction. So raised bog feature extraction based off of the different DEM data sets. So the bare earth and the full feature. So what we see here, this was based off of the canopy height, as I'd shown earlier, which is essentially just the full feature minus the bare earth, as well as some different metrics that we derive based off of the roughness and the homogeneity of the canopy height, as well as the texture or the roughness of the bare earth surface. So again, as we were just kind of talking about in the previous question, the roughness of the bare earth surface can be kind of dependent on the vegetation that existed over top of that surface. So, you know, how accurate we, or how confident we can be that we've actually attained the true bare ground representation within any of these zones can be, you know, determined based on the vegetation that existed within that area. So we had a couple different methods. So we, you know, looked at some of these different landform and textural based methods, so kind of some raster analysis, as well as some computer vision and image segmentation to try to bring it all together. So a bit more object-oriented classification after we kind of derived some of these raster data sets. And this is the resulting data layer that we derived. So if you remember from the previous, the green or the intensity based, it still does a fairly good job, but we're not picking up the entirety of a wetland feature. But from our perspective, that was okay, because these areas are used as seed sources within the wet areas mapping algorithms. So if you remember before, we showed the stream channels, and those were basically defined as the locations that we expect water to be at or near the surface. And from there, we use the topography to iterate through and determine the remaining soil moisture across the landscape. So in a very similar fashion, we can now use these seed sources of bogs to identify the wet features, and again let the model fill in the gaps as they exist amongst this data. So we'll just kind of step through now. So again, this is the depth of water based off of these wetland features. So it does a fairly good job at filling in the gaps amongst them. So we had a lot of noise within the classification or the extraction, but the wet areas algorithms kind of fill those in to, you know, come up with their final result. So what we look at now is, you know, version 2, I guess we'd say, the new methods on the left versus the old methods on the right without any of this wetland feature extraction. And as I had mentioned, we have issues in terms of the raised domes make these features just appear as islands, or as raised islands. And so obviously these wetlands don't appear wet, and they should. So this is some of the advancements that we've made to the model currently. And this is all implemented in the final releases for EMEND that will be coming to you guys very shortly.
So on the raised bog, you attribute a value of 0?
Yes, yes. And we know that that's also potentially problematic depending on how you intend to use the data, because the depth is going to be meters below the peat, right? Nobody has a good idea of what that is because, well, we don't anyway, because this model is entirely topography driven. We don't use any soils data, texture, bedrock geology, or anything like that. And that's always been one of the holdouts that a lot of people have had with using this data, is we kind of tend to ignore a lot of the rules of hydrology, right? We know that there's these other factors that inform hydrological flow across the landscape. But from our experience, both in New Brunswick when we started, as well as when we moved into Alberta here, the field verified accuracies of 70%, they tend to be very conservative, and we have very good correlation just based on topography alone. And we really don't have any other high resolution data sets of these other impacting methods, or like subsurface geology. We don't have nearly at the resolution and precision that we would of the overland flow based on LiDAR data. So to come up with a high precision data set, we just focused on LiDAR. Okay, so now we'll just look at some of the challenges again associated with this. So this is the same area, we just kind of moved to the northeast a little bit. So again, we see in red our predicted bog extraction. Looked great in a lot of areas, but we kind of start to see a bit of a linear feature moving north-south up through here. When we looked at that on an ortho photo, it was a cut block. So similar to the intensity stuff, we can have characteristics of elevation structure or structure of the vegetation or whatever exists on the landscape that can be fairly consistent for the wetland features, but any other features that share that same structure for whatever reason will also be picked up by the algorithm. So, you know, a textural based extraction can have some of these false positives. And they tended to be regenerating cuts from about 10 to 20 years of age. I'm not sure if it was the regen, if it was some of the slash that was left, or what the situation was. But older cut blocks didn't have the issue, younger cut blocks didn't have the issue, but there was just this sweet spot where we tended to have some of these false positives come in, which was a bit problematic for us. So we started to look at, you know, all the forest companies have cut block layers, maybe we can just use that to kick them out. So that was our first attempt at trying to mitigate some of these false positives. But when we started to look at that, they tended to be fairly incomplete and inconsistent. So using them overall, we we weren't very confident in their accuracy and in their full completeness. So what we had to do, well, I guess first off, we'll just have a look. So this is the intensity-based extraction for the same area, and kind of interestingly enough, the intensity-based extraction has the same problems in the same areas as the feature-based extraction. So whatever's happening within this center trail of this cut block, it's fairly closely mimicking, both in intensity and in vegetation structure or elevation structure, the characteristics of the wetland features. And it's not a wet area. We walked it. It's just happens to be a fairly consistent structure. So what we had to do was some manual removals. So we have a student that just kind of goes through and digitizes out wherever we have cut blocks that maintain or contain some of these predicted bog features. And then
Those are they aspen in particular?
they tended to be, yeah.
Okay.
Yeah.
Okay. Yeah, high density, aspen are very high densities at that point. Then canopy is often pretty tight, so
Right.
it's probably similar to, might be similar situation to what you have in the grass.
Right. So that was some of the problems that we had, and we started to look at, perhaps we can start to segregate it by, upland versus lowland associations with this area, because we would expect that aspen are going to be a bit higher on the landscape than some of these bog features, but there was noise associated with that as well. It just wasn't consistent for us. So we just, right now, we deal with the manual removal of these zones, and we've had fairly good success with that. So, once we remove these artifact areas, we can derive our wood areas maps associated with it, and be fairly confident that we've resolved all of these false positives.